Okay, so let's now see what that all looks like. We take the initial pressure, or the pressure of the initial state, to be 1, and its volume to be 1. The volume of the after the isothermal expansion to be 2, and the volume after the adiabatic expansion to be 3. So that's, and then we can calculate the endpoints of all the 4 parts of the Carnot cycle by using the solution of the equations and those values. And so we can plot the graphs. We've done this before, but we'll do it again. So this is the isothermal expansion, and now we go from, and now the isothermal compression is like that. So it looks something like this. So you can see except it goes that way, of course. And now we do the adiabatic expansion, and we get that curve. And now we do the adiabatic compression. Do that. And we put those 4 graphs together, and we get that. So that's the actual Carnot cycle. So so let's now look at the consequences of that. So let's look at the efficiency of the Carnot engine.
And what we mean by efficiency?
Well, we're going to define that in a minute. But basically, if we look at this, up here, heat is absorbed during the isothermal expansion, and some work is done. And then in the isothermal compression, then heat is actually extracted from the system.
Yes.
Right. So the actual useful work, and no heat enters or leaves the system here. So this part is useful work, and this heat can be regarded as waste heat.
Yes.
So the efficiency, we can define the efficiency, well, that's in terms of the heat absorbed and emitted. So the heat absorbed in the isothermal expansion is that, and the negative heat absorbed during the isothermal compression is that, and that can be evaluated by putting in the solution. And so since no heat transfer occurs in the adiabatic process, the net work done must be equal to the net heat absorbed in the 2 isothermal processes. But since the heat exhausted in the isothermal compression must be regarded as wasted, a measure of the efficiency of the machine, of the engine, is the useful work done divided by the heat absorbed in the isothermal expansion. Well, that useful work done is the heat absorbed in the isothermal compression, and then subtracting, remember this is negative, the heat expelled in the isothermal compression. So that's this. And we get this. Now, somehow or other, Mathematica can't work out to cancel this term with this term. So we're going to do the rest of it.
Then you ought to fix that.
Yeah, anyway. So anyway, this is, so we've done this manually. So we'll take that expression and we'll divide those things out. So the result is, for the efficiency, is that, which is 1 minus this. And now that's equal to 1 minus, and now we multiply the on the left by P1 V1 and divide by P1 V1, and then on the right we do the same thing with P2 V2 here. So we haven't changed anything, and now we write it like this. we take this V1 in here, so we've got P1 times V1 to the 5/3 times P2 V2, and we've got P1 V1 times V2 to the 5/3 times P2, which we can move things around, and it looks like that. Now this is just the this is equal to this by the adiabatic equation of state, so we can cancel all that, and the result is this very simple result here. We see that the efficiency is 1 minus the ratio of the internal energies of the high and low energy states. Okay? Well, Carnot's theorem states that no engine can be more efficient than a Carnot engine, and that must be a universal function, and that efficiency must be a universal function of the thermal states of the hot and the cold reservoirs. To see the form of this function, imagine that we build another engine in which the low energy reservoir is now the hot one for another Carnot process to an even lower temperature. If we label this state 3, then its efficiency must be some function F13 of the first and third states, because we traverse the intermediate state twice in the opposite direction. But that efficiency of the combined process must be the product of the efficiencies of the two processes. So we end up with this equation that F13 is equal to F12 F23. And this is what's called a functional equation, and it requires that F12 be some function of the endpoints of the thing. And these functions T1 and T2, which are equal to P1 V1 and P2 V2, is defined to be the Kelvin temperature of the two states, which for an ideal gas is proportional to its internal energy. Thus, assuming it's possible to engineer quasi-static processes, we've succeeded in a purely thermodynamic argument in deriving the temperature function T of V and P of an ideal gas as being proportional to the product PV.
Yeah.
And we haven't assumed anything about statistical mechanics. So let's define this temperature function T fun of V and P to be PV divided by some constant R, and this constant is called the gas constant, and it's to be determined by studying a standard point at which the pressure and molar volume are known precisely, which is the pressure and molar volume of an ideal gas at the freezing point of water under whose conditions, under those conditions, which is defined to be 273.15 degrees. So that molar volume is known, it's equal to that, and the pressure is defined to be 100,000 kilopascals, which is roughly atmospheric pressure, and we get an equation for the gas constant, which is that, and we can solve that for the gas constant R using this, and we get that value, which is the standard value. So I think we'll stop there.
We stop there.
Yeah. Yeah. And in the next lecture, we will talk about how to engineer these processes.
Very good. No.